Homework 1, number 1. What's the reason why there are so many organic compounds? Well, the reason there are so many organic compounds is because of carbon. Carbon has such interesting chemistry, and you likely have studied that in organic chemistry. But carbon can form stable covalent bonds with other carbon atoms, and we can form these enormous frameworks, or we can form really tiny molecules. So it's all because of carbon and the stable covalent bonds it can form with carbon atoms. Number 2, which statement is correct? Well, it turns out all three of these statements are correct. Functional groups are to organic chemistry as polyatomic ions are to inorganic chemistry. They give some sort of functionality to the molecule that they're a part of. Functional groups are the parts of molecules used to organize organic compounds into different classes. That's true as well because, again, those functional groups offer specific reactivity and specific properties to our organic compounds. Functional groups can also be chemically bound or bonded to each other in order to develop larger molecules. That's true as well. All three of those statements are true. Number 3, what is meant by the term saturated when describing hydrocarbons? Well, saturation is how many hydrogens there are when there are only single bonds between carbons. When they're saturated, that means they have the maximum number of hydrogen atoms bonded or bound to the carbon framework. Now, when you have a ring structure, and several people have, in a later question, several people chose the ring structure as being saturated. When you have a ring structure, that actually introduces a degree of unsaturation. So these are chain carbon hydrocarbon molecules. Number 4, identify the correct statement. The alkanes represent one family of organic compounds that is composed of carbon and hydrogen. So alkanes only have single bonds. The ANE here helps us to know that ANE. And we have this carbon-hydrogen framework. That's all an alkane is. Number 5, identify the correct statement. Cycloalkanes are what? Well, they're not saturated hydrocarbons because adding that ring structure actually takes away 2 hydrogens. So it introduces 1 degree of unsaturation. They don't necessarily have a flat molecular structure. In fact, cyclohexane can have that chair or boat conformation. And the third one, compounds that cannot have the hydrogens removed and replaced by chlorine. Well, cycloalkanes can have their hydrogens removed and replaced by chlorine. So none of those statements are correct. Number 6, which of the following formulas represents a saturated hydrocarbon? Saturated hydrocarbon, the general formula is CnH2n plus 2. So the chemical formula that fits that formula is C2H6. Number 7, how many structural isomers are possible for a compound with the molecular formula C4H10? Well, this is a saturated hydrocarbon, and we know it's a saturated hydrocarbon because it fits the CnH2n plus 2. So we have 4 carbons, which means if I put 4 in for N right here, then I would have 10 hydrogens. Now we can form a chain like this. So that's 4 carbons. Remember, there's a carbon at every end and bend. So 1, 2, 3, 4. And I haven't drawn in the hydrogens, but they are implied with a skeletal structure like this. So there are 2 hydrogens here. There are 2 hydrogens here. And there are 3 hydrogens on the terminal carbons. So we have these methyl groups out here. So you can count those up. There are 10 hydrogens there. But the question was how many isomers? Well, if I have no unsaturation, then there are really only 2 ways I can display this. Again, carbon at every end and bend. And it looks like there we go. So there's this one in the middle, and this one in the middle only has 1 hydrogen. Remember, carbon wants to make 4 bonds. And then we have these terminal methyl groups here. Terminal methyl groups each have 3 hydrogens. So we still have 4 C's and 10 H's, but we have 2 isomers. Number 8, the IUPAC name for the compound in the attached picture. Well, I don't have the attached picture here, but the picture looked something like this. Remember, when we name with the IUPAC system, we need to start with finding that longest carbon chain. So I'm going to start up here. And you can go around corners when you're numbering, that's okay. So I have 5 carbons in my continuous chain. So this is a pentane. And remember, I have that A because everything has a single bond. So now that I show that pentane, now I need to look at my substituents. So this is my only substituent, the item that hangs off, and it's hanging off at carbon 3. So the substituent is a methyl, it's at carbon 3, so this is 3-methyl pentane. Number 9. Correct IUPAC name. Again, I don't necessarily get the images, so when you ask a question, it would be helpful if you attached a picture. So the picture looked something like this. Again, the IUPAC name, I'm looking for the longest carbon chain that includes our functional group. Now, it's common to want to name this way to find our longest carbon chain here, and then you struggle to name this bridged part here. Well, we're going to look at that bridge part. That is going to be our ring structure. And because this is a ring structure, that's going to be our parent. So I'm going to number this ring. I'm going to change my color here so that this is carbon 1, this is carbon 2, and this is carbon 3. Then we have substituents we need to handle. We have our methyl group, we have a bromo group, and we have an ethyl group. So when we name this compound, we start with the parent chain, which is this ring structure. So this is a cyclopropane. So now I've numbered it this way on purpose, with carbon 1 being out here on the left, because I have 2 substituents on carbon 1. And I need to decrease the numbers of my substituents. But I'm not going to name this completely yet. So I'm just going to write my substituents here. So I have 1 bromo and I have a 1 methyl, and then I have a 2 ethyl. Now when you go to name with the IUPAC system, you have your substituents like this. We've decreased the numbering. We've met those, but when you put the substituents in order, they need to be in alphabetical order. So I'm going to start with my 1 bromo, and then I'm going to go to ethyl because E comes before M in the English alphabet. So 2 ethyl and then 1 methyl cyclopropane. So that's why that one is named like this. Number 10. Alkanes are blank in water and blank than water. Well, are they soluble or insoluble? Are they less dense or more dense? Well, our alkanes are insoluble. They are hydrophobic. They don't have a polarizable functional group in order to be dissolved in or be miscible in water. They are also less dense than water. Alkanes will form a layer on top of water. They are less dense. Number 11, give the IUPAC name, again, attached image. So the image looks something like this. When I go to name it, I need to start with my parent chain. So I'm going to number it on top first. 1, 2, 3, here's 4. So I have 10 carbons long, and then I'm going to take it, I'm going to number it the other way. I'm going to start here. Now, the object wasn't to get a different number. I went down the same chain. The object was to see where the substituents were going to be with those numberings. So I have my methyl group as a substituent. I have an ethyl group here, and I have this propyl group. So when we go to name this, we have 2 different ways we can name this. And I'm just going to look at the substituents briefly. So here I have a 3-methyl with my green numbers, the ones on the bottom. And I also have a 3-ethyl. Then I have a 6-propyl. Now with the red numbers, the numbers that are on top of my chain, I have an 8-methyl, an 8-ethyl, and a 5-propyl. Well, so we would have 588 or we would have 336. Because 336 is less than 588, we're going to go with the numbers that are on the bottom, the green numbers, and we're going to build our name that way. So we start with our longest parent chain, which in this case is 10 carbons long. They are all single bonds, so we're going to start by calling this decane. Decane is the parent. And it looks like I might be just off screen. So I'll write that down here. Decane. Then I need to put my substituents in alphabetical order. I start with my ethyl. So it would be 3-ethyl, 3-methyl, 6-propyl, and if you were in my organic course, I would expect that to be N-propyl. So 3-ethyl, 3-methyl, 6-propyl, decane is how we would name that compound. Just like that. Number 12. Again, IUPAC name. So for a structure like this, again, we have a ring structure. Now, I am the world's worst artist, but that is supposed to be a 7-membered ring. So this is cyclohexane. And now, how are we going to number this? Well, I'm going to take, again, I'll use green and red inside and outside. So I'm going to do some numbering inside. And then I'm going to do some numbering outside, hopefully with a changing color. So you see with the red, I have 1, 2, 4, 5 tetramethyl. That's on the inside of the ring, and on the outside of the ring, I also have 1, 2, 4, 5 tetramethyl. So it doesn't matter which way you number this, 1, 2, 4, 5, tetra, to show that there's 4 methyl cycloheptane. Now, every one of these substituents gets a number. Doesn't matter that they're the same. Everybody gets a number, and then you need to say how many there are. So 1, 2, 4, 5 tetramethyl cycloheptane. Question 13. Following two structures, what would be classified as what? So the question, we're looking for geometric isomers, stereoisomers, or structural isomers, or conformations. So the structures look something like this. Now we have single bonds here. So immediately that means we can eliminate the geometric isomers. Now for structural isomers, what we're looking for is, are the atoms bonded in the same order? We have our 2 carbons here, and each carbon has 2 H's and a Cl. So we do not have structural isomers. So then we're looking for stereoisomers or conformations. Now a stereoisomer is going to be defined by having an asymmetric center, and that asymmetric center, typically in a standard organic chemistry course, first time through it, you define an asymmetric center as an sp3 hybridized carbon that has 4 different groups attached to it. Here we have 2 hydrogens on each of these carbons. These are sp3 hybridized carbons, and you have 2 hydrogens for each of them. So we do not have stereoisomers. These are conformations. And one way you can confirm that they're conformations is you rotate around this single bond. And when you do that, you can put the chlorines so that they both face the same way. So number 13, we have conformations. Number 14, condensed structural formula for 2,3-dimethylbutane. So this is the skeletal structure for 2,3-dimethylbutane. And what we're looking for is the condensed structural formula. So we need to walk down our parent chain. And what I'm going to do, let's see if I can do it with this one. What I'm going to do is highlight where my parent chain is. So hopefully, when we walk down it, you can see it unfold a little bit easier. So remember, you have a carbon at every end and bend. So I'm going to start right here. This is my terminal carbon. And remember, the hydrogen bonds are implied. So that is a CH3. Then I move down to this carbon. This carbon here has 3 bonds showing. That means he has a CH. He only has one H, but he has this substituent. It's not on the parent chain. Because it's not on the parent chain, I have to put it in parentheses. So CH3, that takes care of him as well. Now I'm going to keep walking down that parent chain and come to this carbon, which is also a CH. I know there's only one H because there are 3 bonds showing. Now he also has a substituent, so substituents go in parentheses, and then again on my parent chain. Now because that parent chain is terminal with a CH3, I can put this 2 here. So this could be the structural formula. Now here on this answer, it doesn't have those CH3s coupled together, and that's okay. It's just another way to see it. I want you to see it both ways because it is possible for you to see that CH3 coupled in as you move further in your studies. This is the answer given that would be correct. Number 15, which characteristic relates to alkenes but not the other hydrocarbon families? Well, that E right there, that alkene, tells us that it has a double bond. And it's the only family, it is the family name. Therefore, that's how we know. Number 16, the IUPAC name for CH3CHBr CH2 double bond CH2. The Br group is located at what position of the compound? Well, first let's draw it. So I start with my condensed formula here. And I know that these carbons are part of the backbone. So I have 4 carbons. There's my 4 carbons. Now, even though this bromine is not in a parenthesis, I know it is a substituent because bromine only wants to make 1 bond. It's not going to be part of the parent chain. So let's walk down this chain a little bit. Here I have my CH3. Then I have a CH, which is here. And again, that 1 hydrogen tells me that that's where my bromine lives. Then if I keep going, this carbon is here. And this carbon is here. Now there's a double bond between these 2 carbons, this purpley color and this green color. So here is my double bond. Now because we name IUPAC by decreasing the number of our functional group first, I know that this terminal double bond is between carbons 1 and 2. That puts bromine on carbon number 3. Number 17, which of the following is the correct IUPAC name? Again, given a following compound, so let's draw it. So this is what that compound looked like. This is not a phenyl ring. This is not a benzene ring because we only have 2 double bonds. We don't have that 3rd double bond. So we need to figure out how we're going to number this. We need to decrease the numbers of everything involved. So first, I'm going to number it this way. Now that puts bromine at 6, and that puts my double bonds starting at carbons 1 and 3. Now this is a diene, so I'm going to leave this here. Now I'm going to number from the inside. What if I start here? Then I have a 5 bromo and I have a 1,3 diene. So the places where the double bonds go don't change. We still have 1,3, but do we have a 5 or a 6 bromo? Because 5 is less than 6, we're going to go with the inside numbering rather than the outside numbering because we want to decrease the numbers of our substituents. So first, let's name our parent chain. Our parent chain in this case is that ring structure, that diene structure. So this is a 1,3 cyclohexadiene. That's our parent. Now let's put the bromine on. So it's 5-bromo 1,3 cyclohexadiene. Number 18 gives you 4 compound names and asks you which can exhibit geometric isomerism. Geometric isomerism is going to be a possibility if we have a double bond that has 4 different substituents around that double bond. So I'm just going to draw them all. So when I had the quiz, I had A was 1-bromo 1-propene. So first I'm going to draw that. Then I had 1-propene. (2,3-dimethylbutene). Well, it's a 2-butene, so it goes like that. So we have our methyls there. And then for my D, I had 1,2,2-tribromoethene. So ethene is just 2 carbons with a double bond there. And I had a bromo here and then 2 bromos here. So remember, geometric isomerism, we need 4 different groups around a double bond. So I'm just going to highlight here, because I have 2 bromos here, it's not this one, because there are 2 bromos on the same side. Here I have methyls on either side, so it's not going to be that one. For 1-propene, remember the hydrogens are implied. Those 2 H's on the same side of the double bond, that means it's not going to be this one, which really only leaves A. Now remember, the H's are implied. There are 2 H's around this double bond, but they're on different carbons. Because of that, the answer is A. This one can have geometric isomerism. So it can be this way with the H's on the same side, or it could be this way with the bromine and the methyl group trans to each other, therefore the H's trans to one another. That's our cis-trans geometric isomerism. When you have different groups, then we start using the E and Z nomenclature. Number 19, we're going to look at the major product resulting from this reaction here. This reaction is a Markovnikov addition product. Remember, the Markovnikov addition product means the bromine is going to go to the most substituted side. Markovnikov is when the H's want to play together. So the H's go where there are more H's. And that's why you form this 2-bromobutane product. Number 20, which of the following is the polymer produced from this? Well, I'll show you how I do. So this was the condensed formula that we were given, the linear formula, basically. When you're forming a polymer, you need to look at where these double bonds are, because that's where we're going to open up. So I'm actually going to draw this way. Now, when I go to make a polymer out of this alkene, I'm going to open up, and I'm not going to use red arrows on purpose because this is not a mechanism. I'm going to open it up this way. And when I do that, what happens, I think I drew that all together. What happens is we open up and we draw a straight line here so that this becomes our monomer of our polymer. So here we're looking for this structure, which in the image looked like it was the second from the left. So it was something that looked a lot like this. Number 21, which is the formula for an alkyne. An alkyne has a triple bond. When you have a triple bond, then you remove an area where you form hydrogens or bond hydrogens. So I'm just going to draw all 4 of these out quickly. Now, just by inspection, we can see, can't change my pen. We can see that these carbons don't have hydrogens to them, but we don't know if they're reasonable structures. We can see that this one is saturated and this is just butane. So we know that this one doesn't have a triple bond. But let's draw these out here. Now, when I draw them out like this with the bendy structure, that's incorrect for when we have a triple bond, but I don't know that we have a triple bond yet. So here we have our H3, and that's, you can see that. Here's my H2. This one shows no H's, and then this one shows 2 H's. Well, that implies that there is a pi bond. There is a double bond here in order to satisfy this, but then we must have some sort of a cation structure, which just doesn't make any sense because there are no H's here, but there are H's next door. So this one just doesn't make any sense. I'm just going to erase it right off the board because it just doesn't fly. Now this one here, we have CH3, CH2, CCH, which does imply that we have a triple bond because we only have the one H here. We have our 2 here and our 3 here. This carbon does have 4 bonds around it, even though I know it's bent and that's incorrect. We're going to hold on to that real quick. So here we have CH3CHC, CH2. The CH2 does imply a double bond that satisfies the octet of this carbon, but because there are no hydrogens around this carbon, again, we're in that weird quasi-state of, well, what's up with that carbon? It doesn't have a satisfied octet. So I'm just going to erase that one right off as well because that doesn't make any sense. So it is this answer here, so let's draw it correctly. When you have a triple bond, what that means is it is linear. So when we draw it, we would draw it like this. Here's carbon 1, here's carbon 2, here's 3, and here's 4. Students oftentimes miss this carbon, but to draw it correctly is to draw it linearly. So that is the answer for number 21. Number 22, which of the following is the correct IUPAC name for this compound? Again, I think it's easier if we draw it because this is awkward with the equals and then this dash. So this is how it was presented, and it's awkward, but it is what it is. So I'm going to draw bendy first, 1, 2, 3, 4 carbons. So I need a butane, and my bromine is hanging off of here. Now it shows a triple bond between these 2 carbons here. So it's very tempting to draw this structure this way. That's incorrect, but it is tempting to draw this structure this way. 2, 3, 4, 5. I think I left one out. 1, 2, 3, 4. I think I did. I think there's another CH2 in here, which means, yeah, I'm drawing it wrong. 1, 2, 3, 4, 5 carbons and a bromine. Looks more like that. But again, it's tempting to draw it all bendy like this with the triple bond. That is incorrect. And we would actually draw this structure like this. So here's carbon 1, 2, 3, 4, 5. So this is 5 bromo 2 pentyne. Remember, we need to decrease the number of the functional group before we decrease the number of the substituent. Number 23, correct name for the compound shown. Now, I want to point out some test-taking strategy. All of these names have propene as the parent name. So because of that, when I go to name this compound or number this compound, I need to number it as if propene was the parent group. So 1, 2, 3 here. We have a 1 propene, we have a 3 phenol. When you have a benzene ring hanging off as a substituent, it's called a phenol. So we have 1 propene. The 1 indicates where that double bond, that pi bond starts. So 1 propene, but the substituent is 3 phenol. So I'm looking for 3 phenol, 1 propene for number 23. Number 24, another acceptable name for 1 ethyl, 3 methyl benzene. So 1 ethyl, 3-methylbenzene looks something like this. If we have just a benzene and we put a methyl group on it, we call that toluene. So toluene, if this is 3, and then I put my ethyl group here, if we start by calling this toluene, then we need to use our ortho-meta para. Remember, ortho is next door, meta is one down, para is completely opposite. So this would be meta-ethyl toluene. That's what we're looking for number 24. And finally, number 25, which of the following could exhibit cis-trans isomerism? Cis-trans isomerism is geometric isomerism. We're looking for something with a double bond. So these were the 4 compounds that I was given. 1,2-dichloropropane, which is here. We do not have a double bond. We will not have cis-trans isomerism. 1-butene, which looks like this. Now we have 2 hydrogens here. So we're not going to have cis-trans isomerism because we have 2 of the same group on one of the sp2 carbons. So that's not going to be it. Then we have propene. This is propene, again, 2 hydrogens on the same sp2 hybridized carbon. That's not going to have cis-trans isomerism. So it must be 2-butene. Now, as I have this drawn, you see the methyl groups and the hydrogen groups, they are in a trans formation. So this is trans, and then this would be the cis 2-butene. So 2-butene has cis-trans isomerism.